Hello, everybody. It's a great pleasure to be here and to welcome you to the second poster session of this symposium. So we are going to present to you now 6 different posters that have been realized by young researchers from different universities, and I will be the first one of this session. So please, next slide. So what I'm going to present today is the work I've been doing in the University of Liège under the supervision of Professor François Remacle about the modeling of dense excitonic manifolds in CDSC nanocrystals for COPAC, so parallel quantum computing. So next slide. So the presentation here is about basically the theoretical work we have been doing on the modelization of the excitonic properties and photophysical properties of these cadmium-selenium quantum dots, and especially toward the goal of ensembles, so ARIES that is more similar to experimental results. So the very simple scheme that I am showing here is basically what we are intending to model. So it is an ensemble of quantum dots where we have a set of pulses, like laser pulses, that are activating one or a dimer of quantum dots or more within the ensemble, and we reach an ensemble of excited and excitons, so we reach their population and coherence and things like this. So this is very important for example, nanotechnologies, spintronics and photonics, solar panels, nowadays it's a hot topic about this, or also spectroscopic experiments like 2D photon echo, which has been a very important tool of the COPAC project. So the advantage of these quantum dot ARIES is that they work at ambient conditions. They're also solid state, and the tunable size of the quantum dot means that we have tunable photophysical properties of the quantum dot. And also an important point is that they have tunable excitonic, they have dense excitonic structures, so which means that they have a dense optical response, which is what we can play with. So how do we build this excitonic structure, and how is it comparable with experiment? Next slide, please. So starting from the single band model, if we take one dot, they have 3 particular states. So we have the electron state and 2 hole states, that is hole 1 and hole 2. Next slide. We can build excitons, so which are the transition between, for example, here, the hole 1 and the electron. I call it the 1s exciton. Next slide. Or the 2s exciton. Next slide, please. So these excitons are very degenerate, and to rate the degeneracy of them, their degeneracy, there is a lot of factors that can play. So here we have included spin orbit, crystal field, and exchange interaction. Next slide. That provides us with a set of 25 excitons. So it's actually quite dense. So some of them are dashed because some of them are bright, some of them are not bright, some of them are have weak transition dipole moments. So F is the main quantum number. So I'm not going into details with this. Next slide, please. So going from the static structure of one quantum dot, what we are doing here is to go to an ensemble. And here I'm taking an example with 2,000 quantum dots. So we have this multiplied by 2,000. The size dispersion is of 7% in this example. And the mean diameter is 2.8 nanometers. So we can see here that we have like an overlap of different manifolds that are from a band, which is blue, and the 2s band that is red here. Next slide, please. So yes, so this is what I was saying. Next slide. And so if I take the energy difference between 2 of the subs, which correspond to the count of energy in the manifolds of my quantum dots, I can get where will be generated the excitonic coherence, given that these 2 transitions have a dipole moment. If they are dark, for sure, I do not build coherences. Next slide, please. Next slide. Sorry. Yeah, I'm sorry. I do not see the next slide arriving. Are you on the next slide? Ah, okay. All right. Oh, okay. I have the next slide. Sorry. So, okay, I will go back from there. So if I can create this kind of maps, which is basically all the energy difference I can get from my manifolds, modulated by the transition dipole moment of the two transitions, which can be convoluted to give this kind of shapes that you see on the figure. And this is actually directly comparable with what experiment can obtain. So if you go to the next slide. Yes, here. So on this slide, we can see that the match between the theoretical modeling of the spectrum of energy differences, which correspond to coherences, is actually quite good compared to experiment. Here, we have these features around 1,000 centimeter minus 1, or like 1,600, and the one at 2,000. So this is a direct proof that our model is actually genuinely able to model very complex experimental data that were provided by our collaborator in Padua, Elisabetta. Next slide, please. So I would like to conclude here after this very quick presentation that we have built during this 3 years a code that is able to model very complex and very interesting quantum dot ensembles. So in them, we can include the structure of the fine structure of the excitons. We can consider ensembles and the size dispersion, which is actually very important to reproduce experimental data. We can work on single quantum dots or dimers if we want to explore the spread of the wave function, for example. But something also that I'm not showing here that is very nice is the modeling of the excitonic dynamics within the systems. And so we can tune some sets of pulses to have the response, the direct optical and the excitonic response of the system after excitation. And what we are able to model, again, it's kind of repeating myself here, but we have this very dense excitonic manifolds. And actually, I was going to talk about biexcitons, but I don't have so much time. But we can also include biexciton to give something that is actually much more dense, and the set of excitons that we can reach is incredibly high, and it's a very nice toy to play with. So we can get the optical response of these quantum dot ensembles, and we can reach some exciton population and dynamical behaviors. So now I would like to acknowledge my colleague, Françoise Remacle from Liège, and the people from Jerusalem and Italy. And now I would like to introduce Giampaolo Marcolin from the University of Padua.
Hello, everybody. My name is Giampaolo Marcolin, and now today we'll talk about my research study on solvent-dependent characterization of fucoxetine through 2D electronic spectroscopy. Next slide, please. So let's start to talk about the system. Fucoxetine is a carotenoid with a carbonyl group, which means that it has an ICT state on its excited state manifold, which is an intramolecular charge transfer state. And it's particularly important for its role in the photosynthesis of brown algae and diatoms. In particular, the ICT state is still a matter of debate today on its nature, whether it is a distinct state from S1, or it is a mixed state, or it has a kind of equilibrium between the two. And its spectroscopic characteristics are strongly dependent on the polarity of the solvent. So we prepare 3 different solvents sample with methanol, acetone, and toluene. And we seek the differences on the ultrafast time scale of this system. Next slide. So these are the 2D ES maps that come out from our experiment. As you can see, there are negative signals, which means that we are dealing with excited state absorption, ESA, and we can see how it evolves from 50 femtoseconds up to 1 picosecond. As you can see, there are 2 different signals, one with the red square, which is attributable to the S1-SN transition, and the one with the circle marker, it is attributable to the ICT-SN transition. As you can see, on the samples, these latest signal drops in intensity as the polarity of the solvent decreases. So on methanol, we see it clearly. On acetone, it is slightly less intense. And finally, on toluene, we don't even detect it. Next slide. So we did a global bi-exponential fitting on these datasets to search for two different time constants to correspond to the main processes of this system, which are internal conversion from DS2 to DS1 state and restoration of the ground state population from DS1 to S0. And we found three different time constants for the ultra-fast internal conversion, which are 65 femtosecond to 250 femtosecond. And this solvent-dependent trend, it is the first time that it's been reported in literature. But the most important things that we acknowledged with this fitting is that if we look at the trace of the signal on the coordinates of the circle marker where the ICT ESA is expected to be, we can see on the low left of this image that it has no rising component, unlike the one of the S1 ESA. Next slide. So this particular thing is new experimental evidence. It's the first time that the ICT state has been probed with this time resolution, and so we can see that effectively it has no rising on its first femtoseconds, which it means that it could be instantly populated without the need of the population of S2 to relax to that state. This could lead to some interpretation. Firstly, as the dynamics are different, DS1 and ICT are two different electronic states for us. And we propose a model to explain this behavior that we found on literature. On a model based on peridinin, where S1, S2, and ICT are mixed together, all of them, and separated only by barriers of potential that could increase or low based on the polarity of the solvent. So if we have a solvent which is polar, like methanol, this barrier between S2 and ECT would be lowered, and thus it would explain why we expect an instant population of the ICT state. This is clearly a first step in the direction of understanding a unique picture of this ICT state, of its nature, and we hope that it could be useful for this other studies in the future. So thank you for your attention, and now I would like to introduce Anna Maria Paniello from the University of Bari.
Okay, thank you. Good afternoon. I'm Anna Maria Paniello from CNR-IPCF. Today I am going to present you my work entitled BODP Functionalized Quantum Dots Architectures for High Efficiency FRET Processes. Please, next slide. The work concerned the fabrication of a high FRET efficiency system, both in solution and in solid state, formed by colloidal cadmium selenide quantum dots and fluorescent BODP dyes. Recently, intensive research has focused on the fabrication of quantum dot-based organized hybrids in solid state, which have shown new properties due to collective interactions among nanoparticles or at the interface with molecular dyes. In this context, properly synthesized amino-modified BODP dyes are used in virtue of the high affinity of amine group in coordinating the quantum dot surface for providing an effective coupling between the donor, the quantum dots, and the acceptor, the dye. Please, next slide. To fabricate the coupled nanohybrid, a modification of the surface chemistry of the quantum dots has been applied. Specifically, a partial exchange of the native capping layer with the ethanol amine has been carried out. The ethanonamine is a short bifunctional linker that allows at the same time the dispersion of the quantum dots in a mix of polar and apolar solvent with the dye, and also free the quantum dot surface to allow the anchoring of the dye. Then the functionalization of the quantum dot by the dye has been obtained by mass action. From the FTIR measurements demonstrate the effective linking of the dye at the quantum dot surface. Please, next slide. In the nanohybrid, the energy transfer can be demonstrated by the changing of the emission of both chromophores, the slight shift of the fluorescence and the strong modification of the time-resolved decays, namely a faster recombination for quantum dots and a slower decay of the dye, testified interaction and the energy transfer process. From the FRET theory, it is possible to calculate the Foster distance and the quite high efficiency, 76% in solution. Please, next. Okay. We tested the couple system also in solid state, deposited on a substrate by drop casting. Even in this case, the quenching of the fluorescence of the quantum dot in the nanohybrid and the faster recombination dynamics demonstrated the energy transfer with a calculated efficiency of 80%. Here on the right, I reported the theoretical curves of the FRET for the nanohybrid in solution and in solid state. The measured efficiency are shown as points on the curves. Here, demonstrating the FRET mechanism between quantum dot and dye. From the equation of the right, corrected for the theoretical number of the dye acceptor for each quantum dot, obtained by applying a Poisson distribution to the PL decays, it is possible to calculate the donor-acceptor distance that, taking into account the size of the quantum dot and the length of the amino spacer of the dye, confirms that the dye is effectively coordinated to the quantum dot surface. Please, next slide. In conclusion, I demonstrated efficiency FRET processing, quantum dot amino substituted quantum dot dye in solution and in solid state. The preparation strategies can be applied to nanoparticles of different size and composition to obtain new and original coupled system for developing sensor devices and, due to the reduced distance, to explore possible coherent effects in the energy transfer between two fluorophores. Please, next slide. Finally, let me thank the project that founded this research, the collaborators listed here, and all of you for your kind attention. So now let me to introduce you Anna Friedman from the University of Jerusalem.
Hi, my name is Hannah Friedman. I'm from the University of Jerusalem, from Israel. Okay, so I want to talk to you about coupling between quantum dots using chiral molecules. Next slide, please. Okay, so I prepared a multi-layer structure of 3 sizes of quantum dots. I used 3 sizes for having an energy direction, and I use chiral molecules as linkers. The reason I use chiral molecules is because they showed spin filtering, and I want to see how it affects on the coupling between the dots. For a reference measurement, I prepare the same structure, having a detailed molecules, non-chiral linkers. So to test the effect of the chiral molecules on the coupling, I use a circular polarization. Circular polarization to excite the sample. So I can, by using the circular polarized light, I will manipulate the spin that I'm exciting. Then I measure the sample in a lifetime system, and I'll show you in the next slide the results. Next slide, please. Okay, so here we can see that for the left circular polarization in the red line, in the upper slide, we can see that for the left circular polarization, we get the shorter lifetime compared to the right circular polarization. And if we compare the sample with the chiral linkers to the non-chiral linkers sample, we can see that the scientific difference is shown only for the chiral linkers. And this shortening is in for delocalization that happened between the dots. And because of that, I try to measure also the absorption spectrum. And I show you the result in the next slides, please. Okay, so here we can see the absorption spectra of the chiral linker sample and the non-chiral linkers. We can see that in the chiral linkers, in the red line, that is the absorption measured by exciting the sample in left circular polarization, the red line, we can see that there is absorption broadening. What we don't see in the non-chiral linkers sample. So this result, together with the previous result, is showing delocalization. Next slide, please. And so we have the specific spin state that we excited by the circular polarized light, and also we prepare a sample that having 3 sides of quantum to have some energy direction, and thus we get a preferred spin. And we in the measurement we see that we get shorter lifetime and expansion of the absorption spectra, and this is showing delocalization. What we get here is a stronger coupling by manipulate the polarization of the light. And that's it. Thank you. And I would like to introduce Ksenia from the Hebrew University in Israel. Thank you.
Hello, everybody. My name is Ksenia Komarova. I'm from Hebrew University of Jerusalem in Israel, and I will talk about our joint project with the University of Liège with a group of Professor Françoise Remarque and Hugo, who is present here, on the first realization of the quantum computation for vibrational dynamics. Next slide, please. So what we use as a device is a solid-state array of semiconducting quantum dots, which already is mentioned by previous speakers. And the device is addressed by 2D electronic spectroscopy. And in the computation, what we use is actually this time delay, big T, between the second and the third pulse of the 2D electronic spectroscopy setup. Next slide, please. So the main idea is to use the observables of the device in order to compute the observables of the physical system. As a physical system, we took the kind of most simple example, but not that simple as just harmonic oscillator. We use the triatomic molecule, for example, CO2, where each bond is a local bond, so we describe it with the algebra of creation and annihilation operators, but they are coupled by this one phonon coupling scheme, and we want to compute various observables for this system. For example, energy transfer between these two modes because they are coupled, so the transfer can happen, or bond distance variation due to perturbation or something, or even dispersion in the bond distance. How we do that? We have in our device pure electronic Hilbert space, so we don't have vibrational dynamics there. How we do it? We already saw in the presentation of Hugo that in the electronic structure of the quantum dot, we can define, for example, 2 excitonic energy levels. These are shown on the left, S1 and S2. And for low resolution readout, we can maybe only decipher them. But even already with the experimentally available scheme, we can get an intermediate resolution with the 4 energy levels resolved. And in the 2D photonic experiment, we can observe coherence beating between all these levels. And it is our pulse setup that will tell which coherence will be created and which coherence then we can track and use in our computation. Next slide, please. So here's an example for the energy transfer computation. It is provided by matching the beating frequency of the coherence here for level 2 and 3 of the quantum dot with the frequency of the oscillation of the energy transfer. Here it is, for example, 500 wave numbers for CO2. And how we do it? So we go to the 2D frequency map and we step from the off diagonal on 500 wave numbers on this particular frequency, and we see the peak. Here the maps are computed already for the averaged ensemble of quantum dots, so we don't see one specific signal from one dot, but it is average of the ensemble. That's why we have dispersion in the band structure. And so along the big T, the signal is changing in time exactly in the same way as our physical observable is changing in time. So that's the mapping of the observables of the physical system and the device. In these two papers, there are more observables discussed and how the scheme can be generalized for any other closed algebra. And I think it's a promising beginning of the quantum computation. So with this, I want to thank organizers of the symposium and introduce the next speaker, Edoardo Amarotti from University of Padua.
Sorry. Thanks, Xenia. Good afternoon, everybody. I'm Edoardo Amarotti, and I'm attending my master's degree at the University of Padua under the supervision of Prof. Elisabetta Collini. During my master thesis project, we focused our attention on cadmium-selenide quantum dots. In particular, we tried to understand if it is possible to generate and follow in time quantum coherences by 2D electronic spectroscopy measurements. Next slide, please. In this work, two samples in a liquid dispersion of hexane were analyzed, one of monomers and one of dimers. The monomeric quantum dots have an average diameter of about 3 nanometers, and they were obtained by colloidal synthesis. Instead, the dimeric quantum dots were obtained by linking two quantum dots through propandiol with a nominal length of 0.5 nanometers. In the dimer, the quantum dots interact, leading to the formation of new excitonic states. They localized on both dots forming the dimer, as visible in the diagram. The dimeric samples will then produce a rich 2D ES responses that can be exploited to develop quantum software. In the first slide, we can see the results. Please, next slide. First, preliminary characterization were performed through absorption spectroscopy and fluorescence spectroscopy. In this way, the excited states structure of each sample were preliminarily identified. This allowed determining which states were accessible by the laser band used to record the 2D ES measurements. For both the samples, only the first excitonic state manifold is accessible due to the laser limitation. Now the discussion is focused on the interpretation of the data obtained. For both the samples, the 2D maps shows a positive peak on the diagonal, attributable to ground state bleaching and the stimulated emission phenomena of the first excitonic transition. Due to the size distribution of the sample in solution, the peak is stretched in the direction of the diagonal in the rephasing map. This effect is defined as inhomogeneous probing and depends on the size distribution of our samples. Now, the oscillating dynamics are analyzed to verify the presence of coherences in the dimeric samples due to the coupling between quantum dots. We apply the time frequency transform at well-defined coordinates, as visible in figures, to observe the oscillating features. In the low diagonal peak of the 2D map, we reveal the intradot coherence for the monomeric sample at 900 centimeters to the -1, and an interdot coherence for the dimeric sample around 800 centimeters to the -1. Instead, in the high diagonal peak, only the dimer sample shows a feature around 800 centimeters to the -1 that can be attributed to the interdot coherences between quantum dots. In conclusion, in the next slides, we can say that quantum dots can be effectively used to achieve rich 2D ES responses, which can be exploited to develop quantum software. Thank you for your attention. Now we can attend the conference of Professor Collini, COPAC, Coherent Optical Parallel Computing. You just have to click on the link present in the chat. Goodbye.
Bye.
Bye. Thank you.